Hello, today we're talking about work, and this is going to be our lesson, what we're talking about concerning work. And everybody knows what work is. It's something that tires us out, right? So we know that whenever we do work, energy has to be expended. And in physics, we talk about doing work on certain objects. So to illustrate what we're talking about, I drew a crate or a box, and I have two people involved in our little example over here. Let's say this guy over here pushing this box across the floor is me. So this is going to be me. And I'm pushing over here this box, and you are going to be up here. You are just standing doing nothing, standing on top of this box. And I'm going to push with a force, choose yellow. So let's say I'm going to push with a force this way. I'm pushing with a force this way. So this is the force that I'm going to push with. And we'll call it 1. Force 1 is going to be for me. And you are going to be standing up on top of here, and your weight is going to be pressing down on this box in this direction. So here you are pressing down force 2. You're pressing vertically down by standing on the top of the box. And now what's going to happen is the box is going to be moved from this position to, let's say, this position right here. So here's our new position of where our box is. Let's say now the box is going to move from here to here, and let's just, for example, let's say we moved it 10 meters. So it moved 10 meters from here to here along the floor. Now what I'd like you to look at is that the force that I'm applying on the box in yellow, I'm pushing it parallel to the floor, and I'm moving it 10 meters from this position to our final position over here. I'm doing work. Now my question is, are you doing any work? Well, you're just going for the ride, right? So you do no work. I'm doing all the work because the force that I'm applying to actually move the box is parallel to the movement or the displacement of the box. So which is, remember we talked about displacement a couple of chapters ago, and displacement is the change in position. So we can think of displacement, our displacement, as the change in position. And displacement, if you recall, was a vector quantity because it went from position 1 to position 2. So our displacement is in that direction. Actually, it's 10 meters in that direction. That's our direction, and that's our displacement vector. Notice that my force here that I'm applying to the box is directly in line with the displacement, and that's going to cause me to do some work on the box. Your force is just your weight on top of the box, straight down, perpendicular to the displacement. So you see your force, or force F2, is perpendicular to the movement of the box, and as such, as you might expect, you are doing no work at all, and you're probably not going to be very tired. Even if you stood on your hands and you were pressing down, you're still doing no work because the box is not moving in any direction whatsoever of your force, F2. It is simply moving perpendicular to it. So I'd like to define work right now, and we're going to give us a definition of work. Work is going to be equal to the force applied times the distance or the displacement that the object that you're doing work on moves. In this case, we have force F1 is working parallel with the displacement, and the displacement is 10 meters. So let's give a number here. Let's say my force F1 was equal to 10 newtons. Let's say we had applied a 10 Newton force to this crate, and it moved 10 meters in that direction. Then the work would be 10 newtons that I applied for a distance or a displacement of 10 meters. And we see that for the work, we're going to have 10 times 10 is going to be 100, and our units are going to be newtons times meters. So we see immediately that work has units of force times distance. And we call a newton meter something called a joule. So 1 newton meter is 1 joule of work. 1 joule of work. That's the unit for work is the joule. And it's the amount of work done by a force of 1 newton and moving an object 1 meter. Here we have 10 newtons of force. We moved it 10 meters, so we have 100 newton meters, or 100 joules of work. Now, I said at the beginning that you were standing up here perpendicular to the direction of the displacement, and you did no work because your force was perpendicular. That leads us to understand a very important fact about calculating work. Work, more precisely, is the force times the distance or displacement times the cosine of the angle between the force and the displacement. So let's give an example of what we're talking about here. Well, let's see. I will use green because that's a cool color here. All right. Suppose, like in my example, my force was in that direction. So let's say your force is in this direction, and let's do pink for displacement. Your displacement, D, is in the same direction, lined up. Well, if you look at these two vectors, they're absolutely parallel to each other. What is the angle between the force vector in green and the displacement vector in pink? The angle here, theta, is simply equal to 0. And the cosine of 0 is 1. And the cosine of 0 is equal to 1. So therefore, in this case, where the force and the displacement are parallel to each other, you say work is equal to force times distance times the cosine of 0 degrees, and that's simply going to be force times distance because this guy becomes 1, or is 1, simply 1. Now, let's get back to the other example where you were up on top of the box over here, applying a force F2, that was you, by standing on the box, and the displacement was actually going that way. Here's where your displacement went. In other words, the box moved parallel along the floor, your force was perpendicular to it. What is the angle theta between the force and the displacement vector? Well, if you look at those two vectors, and you could put them in this fashion, you could always put them tails to tails there. The angle between here, this was a right angle, right? The force and the displacement vectors were perpendicular to each other, so this angle here is 90 degrees. So the work done would be, I'm sorry, this is F2, would be F2 times the displacement, which was 10 meters, right, times the cosine of 90 degrees. Now the cosine of 90 degrees is 0. Therefore, the work done by any force that's perpendicular to the displacement is going to be 0 because the cosine of 90 is simply 0. So what we wanted to say here, and I'll put it over here for us to remember, let's do it in light blue. How about that? Our new formula for work is that the work is going to be Well, actually, I put it right here. Here's what we want to remember. Work is simply force times distance, where force is a vector. Distance or displacement is a vector. Displacement is a vector. They have directions, and theta here is the angle between the force and the displacement. So in other words, if you look at the direction your force is applied and you look at the direction of the movement of your object, there'll be some angle between it. In this case, when they're lined up parallel, the angle in this case is going to be 0. So cosine of 0 is simply 1. And in that case, work simplifies to force times distance, because the cosine of 0 degrees is 1. If the force happens to be perpendicular to the displacement, then there's 90 degrees between those two vectors, and the cosine of 90 happens to be 0. Therefore, the work is 0. There's no work done. So what we want to say is work is simply going to be force times distance when the force you're talking about and the displacement are parallel in same direction and equal to 0 when perpendicular. And we'll come back next time with the next video and take this a little bit further.